Hello guys, welcome to my channel. Today let's see about radar antenna and what are the different types and how they are used, how to calculate how they are calculating the distances now. So coming to the radar antenna. So actually the radar antenna is a distinctive and important part of any radar. Yes, that antenna we can't transmit or receive anything. So it serves the following functions: acts as a transducer between propagation space and guide wave propagation in the transmission lines. Why it is called a transducer? Because firstly it is it will transmit and receive. This antenna has the capacity to transmit and receive, so that's why it is called transducer. Basically both will be present for only single antenna. Now concentrates this radiated signal energy in the direction of a target. Okay, next collects the echo signal scattered back to the radar from a target. Next, measures the angle of arrival of received echo signal so as to provide the location of the target in azimuth and elevation or both. Acts as a special filter to separate targets in angle spatial domain, and rejects the undesired signals from direction other than the main beam. So it will help us to basically filter the signals that are coming from other targets rather than what you are main focused on. Provides the desired volumetric coverage of the radar. Okay, it will also tells us how much it will cover the entire area. So usually establish the time between the radar operates observations of a target. Revisit time, we are calling that. So this is how. Next, coming to the antenna parameters. These are the few antenna parameters that is needed. One is direct to gain, that is denoted as GD, power gain G, antenna radiation pattern, effective aperture AE, side lobe radiation, aperture efficiency ρA, polarization. Now let us discuss one by one. So direct to gain or the directivity, it is also called as directivity. Antenna gain is a measure of ability of an antenna to concentrate the transmitted energy in a particular direction. That's what you already know this. Coming to the formula, GD is equals to maximum radiation intensity by average radiation intensity. Now this average, basically we are mentioning this in the theta comma d format, theta comma phi, which is called spherical coordinate system, and it is denoted by that values, the power of the values that will be denoted by p of theta comma phi. It is a function of theta comma phi, watts per steradians. But the average energy here, the average radiated intensity is again formulated as total power radiated by antenna by entire solid angle of the 4 pi steradians. What is solid angle? Solid angle is basically, in 2D we'll call it as angle, but in 3D object we'll call it solid angle. For example, let us take a 3D object, something like this, and the angle that is made here. Okay, it's somewhat difficult. I'll show you using some examples. Solid angle. So you can see it's like a this. Okay, 3D. Oh, okay. Now let's come back to PDF. So that is what 4 pi angle of 4 pi steradians. Now we substitute all those in this GD equation and we got as 4 pi into maximum power by total power radiated. Now substitute this for maximum power and total power formula here. Maximum power will be that in the function basically at a particular value of theta comma phi, the function of p of theta comma phi will be maximum. So that value, that is he is saying, that is maximum power. To find the total power, what we'll do, we'll just integrate this p of theta comma phi function, that is a power function, with define d theta and d phi. We'll get that value, total value of the power radiated. So what we'll just do is we just equate this to 4 pi by beta. To 4 pi by b, where this b is called beam area, and this b is when you compare these two equations, that b is equals to this term divided with the p of theta comma phi max. Okay, Now, after approximating the derivative of an antenna, and it can be written as basically after like calculations and all, we got as GD is equals to approximately is equals to 2600 by theta b into phi b. These theta b and phi b are all half power beam width. Okay, half power beam widths, and they are in degrees. They are measured in degrees. Okay, the problem is given, just they have given this two half power beamwidth values, and just you need to substitute in that equation and we will get this answer. Now power gain. What is power gain? So power gain is the defined as the power it is the ratio of maximum radiation intensity from subject antenna by radiation intensity from a lossless isotropic radiation with the same power input. So basically, when you write for the ratio, we will get as G is equals to rho R into GD. Okay, the relationship between GD and G can be written as G is equals to rho R into GD, where rho R is equals to radiation efficiency. Now coming to the problem, like we substituted, we need to, the G value should be in some numerical decimal value, not in dB. So you need converted using 10 log G is equals to 35, and we got G as this much. And it's okay, same problem. Now coming to the third point, that is antenna radiation pattern. When it is an isotropic antenna, we'll get a perfect spherical radiation pattern, but when it comes to direct to antenna, it will be have some these lobes, having some lobes, where one is will be the main lobe and other are side lobes, and there is some more smaller lobes which are positive due to the leakage. So when you observe with respect to degree of axis and the relative radiation intensity, this is how it will look. Basically, if you observe this graph in terms of angle, that means let us take this like around that angle. Basically, if you take and if you watch from this side, you will be like rotate like see, move from clockwise and all, like at every angle how it is changing. So at initial zero, it is the main lobe. When you go on rotating clockwise, sorry, anti-clockwise or what, basically increase the angle, basically 20 degrees, 40 like that. So what happened, there will be some decrease like that. So every peak has some names given. So just allocate it. That is the vestigial lobes or shoulder, we'll call it. It is the first side lobe, other minor lobes, split over radiation, and back lobe. Now effective aperture. What is effective aperture? It is the effective area where basically we can simply is the measure of effective area presented to the incident wave by the antenna. Basically, we can also another term we can say basically it is the product of antenna aperture efficiency into the physical area. A physical area will be like normal rectangle. Let us take a rectangle. They will be given length and breadth. So what we can find here, that is length into breadth. That is the physical area. So to find the effective area, what we'll do, that area will be multiplied with this effective antenna aperture. So antenna aperture efficiency will multiply and we will get AE. That's it. This is the relation between G and AE. Okay. So now coming to the side lobe radiation, this is also seen. So sometimes what happens, if there is a side lobe is like as the side lobe gets increases, the main lobe gets increases, the side lobes will decrease. Okay, it will be like this. So when you compare, when it is this direction, those side lobes are like this. When the main lobe is too large, this will become small. We are in like inverse in relation. Now the lower the side lobes, the lower will be the antenna gain and the aperture efficiency, and the greater will be the width of the main lobe. That's what we see. The lower side lobe decreases, the antenna gain also decreases. Okay, and also aperture efficiency also decreases. Width of the main lobe also will increase. So low antenna side lobes are designed in a radar so as to avoid detecting larger targets when they are illuminated by the antenna side lobes. Okay, basically when you have low antenna side lobes, then they won't detect the other targets. You understand? Because if it is so similar as a main see, if you observe this, it is significantly relate. We can relate these to the sizes of. We can relate the size of these main lobe and side lobe. So what happens if this hit the target and the echo signal is received, and it will also detect that also. So our aim is to how much however possible to minimize this side lobes. But also you need to see here antenna gain is decreasing, so again there will be a trade-off. So you need to take as a suitable value. Take the suitable values. Now aperture efficiency. Aperture efficiency, it is the capacity of the antenna to capture the incident echo signals. So what is means when rho a is less than 1, basically it means that the part of the echo signal is not picked, and also radiated energy is redistributed in angle rather than the dissipated. So basically what it rather dissipate the radiated energy rather dissipating, it will redistribute it. Okay, so basically it should be dissipated to surroundings, right? Basically it should be nullified, but rather what happened, it is redistributed, that basically that values are getting added or subtracted to the other lobes, the other energy forms. Next, polarization. What is polarization here? The polarization of a electromagnetic wave is defined as the orientation of electric field or parallel to magnetic field. Okay, so types of polarization. So in the types of polarization: horizontal polarization, vertical polarization, circular polarization, elliptical polarization. So this is the types. Now coming to reflector antennas. Okay, reflector antennas, where there are different, like this is one of the type of antenna. We can see it is like a concave mirror, where there will be a focal point. When the light is emitting from the focal point, that it hit the surface, concave surface, and the rays will become parallel. That they will reflect it in a parallel fashion. So that is one of the use. So you can also see this in TV antenna dishes, where you can see that there will be a dish and there is like a torch type antenna. Basically it's a transmitter. So it will what it will do, it will emit the electromagnetic waves onto the dish, and the dish is in such a way that it will make that reflector waves it will make that waves in a parallel way. It will transmit them in a parallel beam. Okay, so when you see all this at once like a plane, it is like a wave front. We call it as like a wave front, and the position of the source can be vary. So there are three types here seen. One is a rare feed using half wave dipole with a parasitic reflector. This first one. So here what happens, there will be a source here, the dipole will emit these waves and it will make them to parallel. Now what happened to the other half, like they not only go in this direction, right, they also come in the upwards. So what happened, this parasitic reflector, what will it do, when it hit this plate, it will again reflect this to in this direction. It will hit and reflect it to hit like this. Got it, right? This is how you need to how that all works. Now coming to rare feed using horns. Rare feed using horns, here the position of the horn can be two types, either it is like a rare feed or front feed. So rare feed is like from the back, and front feed is given like this. This is one example, real life antenna. Now coming to this curvature, okay, curvature and the focal length, how much it should be, so how much what is the preferred value of that antenna curvature. So generally there is a ratio f by d, that is focal length by diameter of that reflector. That ratio f by d should be lies between 0.3 to 0.5. Okay, in general. Offset feed reflector. In this offset feed reflector, the reflecting surface will be on somewhere and the feed will be on somewhere. So what will happen? It will basically like project these waveforms onto the pulses onto this reflector, and it will make them again into parallel. Okay, this parallel thing is only purely of reflection properties. Okay, so that's all. Like if you change this feed, and you can also change the direction of the parallel beam going like up and down like that. So cascade antenna. What is cascade antenna? Cascade antenna, where we'll have the feed in the center of this mirror, in this reflector, and there will be another convex reflector, that is called hyperbolic subreflector. What will happen? All the waves will be shoot over this reflector, and then it will in turn reflect them onto the main parabolic reflector, and this will again comes to parallel. This is one type. So geometry of cascade antenna, this is like the geometry where this when you join these points, now it will be exactly like this. It is a part, and then you have to take this much like that. So and again, the one more cascade is polarization twist cascade antenna. Like actual what happened, there will be one more layer over this reflector, a polarization layer for the subreflector and also for this, and according to the property of that polarization surface, depending surface, it will go here. What will happen? A horizontal polarized wave is sending, and this is like it is if it is a horizontal only, it will only send back the horizontal polarized wave, and this it is like think it is a vertical polarized layer. So what happens? There will be a twist. Okay, this horizontal will be twisted to vertical, but that's why it is called twist reflector. It will change this horizontal to vertical, and it will transfer. Parabolic cylinder. So parabolic cylindrical antenna is like, if you observe this shape, okay, it is looking like a part of a cylinder. Okay, you can see it is a part of a cylinder. That's what. This is a part of a cylinder. Next, coming to electronically steered phase array antenna. So let's come to the array antenna. Here coming to the array phase array antenna, like there will be like many antennas placed. So why it is called array means basically there is in future there will be two-dimensional antenna array. This is a one dimension, so there will be linearly, so they will be arranged in one by one, side by side. So they are separated by distance d, and the rays, the incoming signal is so the reference line is this one, and the angle of the signal coming hitting is like this. So angle is like theta. We need to measure like this. Okay, so on and this is the total voltage, that is EA. Okay, that will be divided. Basically this coming signal will be E1, E2, E3, so on, En. That voltages will be getting summed up, and the total like this will be they will be summed here, and again this point, and the entire thing will be summed at this point like that. So n element receiving parallel feed, this is called n element receiver parallel feed linear array with the equal lengths of transmission lines between each antenna and antenna output. Now what is the advantage of this? Okay, why you are going for this? Or electrical phased arrays are interested because they can provide rapid beam steering. Agile is also the same thing, meaning is speed, like quick basically. Potential for large peak and large average power. Each element can have its own transmitter, and the power aperture producing can be large, especially at the lower frequencies. And multiple target tracking, we can track multiple targets at once. So this can be accomplished either by generating multiple pulses simultaneously or independent beams, by rapidly switching a signal beam to view more than one target in sequence. So next, a convenient means to employ solid state transmitter. Okay. Next, convenient shape for flush mount or for blast hardening. Now, control of aperture illumination because of many antenna elements available at lower radar cross sections, if possible, design. Okay, so basically at lower we need a lower RCS. So it is possible, it is properly, if it is properly designed, this array, antenna array, we will get lower radar cross section. Operation when more than one function. So basically these antennas can be used for not only for a single purpose, we can use it for multiple functional radar. So let us look into the maths behind it. So let us take two antennas here separated by distance d and a target which is at a distance r from radar to antenna 2. So now there will be two cases. Let us take two cases. One, that the signal is coming 0, that means like this, and one like this one case. The another case is like 90 degrees perpendicular to this line. So so let us take for 90 degrees for now. So we can see that this target is at a distance of r from the antenna 2, and from antenna 1 it is a distance of d plus r, right? Okay, we wrote those two, and when therefore it is theta is 90, the difference between the signal path, to find the difference between the signal path, we need to subtract these two, 2 minus 1. We got d plus r minus r, that is this d1 minus d2. We subtract what we got, d plus r minus r, that is d. So similarly, when theta is equal to 0, that means when the theta is equal to 0, in the sense both are in the same direction. So basically it will be like this. A target is there, some target or something like this, target is there, antenna is there. Okay, some antennas are there. Now it is also coming like this. So both this target is at a distance r only for both of the signals, so both of the antennas. So what will happen, d1 is equals to r and d2 is equals to r. When you find the distance separation, what happens, it will become 0, r minus r will become 0. So signal path difference between the signal path will be 0 when theta is equal to 0. So from this two, what we can observe that it is changing that difference in the signal path changes with respect to theta. So from that equation, what we can say that we can formulate an equation, that is f of theta is equals to 0 when theta is equal to 0, 1 when theta is equal to 90, and when it is between 0 to 90, the value also become from 0 to 1. So basically when you observe this expression, this is the expression for sine theta. So sine theta, so what happens, the original formula for finding the difference between the path, okay, signal path, will be d into sine theta. So if you know that angle, how much it is incident on the antennas, we can find the signal difference between the signal paths. Now coming to the phase difference between the adjacent elements. Now phase difference, basically phi is like beta l, you know that. So beta can be written as 2 pi by lambda. What is the l? L is the distance in the signal path, that is what d is sine theta, right? So that's what we substitute. We know the phase difference, phase difference is beta l, where beta is 2 pi by lambda and l is d sine theta. Substitute and we got the expression. Now lambda is the wavelength of the receiving signal. Now assuming the amplitude of the received signal at each element be unity, okay, amplitudes, like the amplitude be unit, let us assume that the sum of all the voltages from the individual elements when the phase difference between the adjacent elements is phi, can be written as sine wt plus phi Sine wt plus 2 phi, so on, sine of wt plus n minus 1 of phi. So when we sum all these voltages, what we got an expression like this: sine of wt plus n minus 1 of phi by 2 into sine n phi by 2 into sine phi by 2. So that is the EA value. That means this value. Okay, that means every antenna has different phase. That's what. But changing like what you call arithmetic, changing in arithmetic progression only. So it's fine. So next, that's what we found that expression. Now, where W is the angular frequency of the signal. Okay, N is number of antennas. E is the total. Okay, total sum of voltages. Okay. Now coming to two array elements. Let's take two array elements and space the distance apart with the received signal arranged at an angle theta naught, because it was measured with respect to the broadside direction. Okay, beamwidth steering based on. So basically how it is come d theta, basically that's the trigonometric. So it is theta, and again if you draw the line, it is again theta, and the dot line is 90. Like that we got this will be theta, and we found that this is d, so this will be d sin theta. Okay, based on true time delay, a beam steering using a phase shifter, that is a variable over the range 0 to 2 pi radians. So basically what we do now, we need to shift turn the beam. Okay, we need to turn the beam or to rotate the beam. Okay, to do that or to steer that beam, what we can do, we can just have some one more element here, that like it can be steered using two methods. One is by using time delay, and other is by phase shift. So for certain value of theta degrees, the value for time delay will be d by c sin theta. C, so for sin theta naught, c is the light speed, and d is the distance here. Now coming to the phase shifter, to have some a deviation of theta naught, the phase shift should be 2 pi d by lambda psi theta naught, sin theta naught. Okay, now coming to the types of arranging of these arrays. One is they can be arranged like serially. Okay, parallel they can be arranged in parallel feedback. So you can observe that is one will be 5, another will be 2 5, 3 5, so on, like that, what you have observed previously. Now it can be in serial feed from one end. This is one end, like that. So from one end, so now all this will be having the same phase 5, and there will be also serial feed from center. From center will be feeding, one will go to this direction, one will go to this direction, like this. Now coming to the planar array of scanning. Now only the previous lot only one axis, x-axis, like it is only the one dimension, x dimension. Now we will also have the y dimension also. It will be like a matrix form. So this is how we will be arranging all these arrays. And high power. Okay, now comparison of a passive and active aperture array. Okay, passive and active aperture FA configuration both shows the subarrays. A is the passive aperture phase array, which is a single high power transmitter on the left and a high power phase shifter on each of the element. Okay, for each of the element there will be some what the phase shifter will be there. See, you can see each of the phase shifter is there, and also a high power phase shifter, basically what is meant. And then for it is B, it is the active aperture array with T by R transmitter transmit by receive array or transmitter or receiver module at each element. Okay, there will be transmitter receiver module at each element, and then sometimes these might be the signal bandwidth. Okay, sometimes there might be booster amplifier on the transmitter at each subarray, that is the bypass on receiver, okay, bypass on receiver, and or a time delay element for increasing the signal band. Anything can be placed over there. Now T-by-R module. So C is the T-by-R module configuration with a power amplifier on the transmit and a low noise amplifier on the receive. So this T-by-R, here this T-by-R can be modeled like this. There will be a transceiver switch, transmitter receive switch, amplifier, power amplifier, and there is another thing, another transmitter receiver switch. So like this is LNA, that is a low noise amplifier, okay. Like this will happen. One phase shifter is there. So there are few practical antennas. This is a ground based radar, this is a ground based radar, and this is one type of radar, active aperture radar. This is like a mechanically steered planar array antenna. And one more thing, one more type of antenna, this is called pulse Doppler radar. Now coming to the cosecant squared antenna pattern. Cosecant squared antenna pattern, basically the reflector will be in the form of the different bent parabola. It will be looking like a bent parabola in such a way that we can bend the reflector in whatever way you want. So if you bend in such a way, if you want while bending that, we can define the direction the array should be focused on, okay. It will be this. So when like in one position it is like this, and after I bend this edge, and it is the change that they change the direction, okay. Next, coming to the graph where it is showing that pattern, okay. This is the pattern, like in the direction line, what is the pattern? It will be like this, and there will be some like some side lobes over here, like that. When it comes to cosecant antenna, it will be cosecant squared antenna. It will be like this, okay. This is the constant height, okay. That's it. Now what is coming to the lens antenna? In lens antenna, instead of reflectors there will be lenses. The same optical physics what happens over here, over the lenses, that will happen here also. The waves will have coming from here, and it will be coming like parallel. When we have some parallel beam incident on the lens, they will be converge for a convex lens. Depending on the length, if it is convex, they will diverge like that. This is a plano-convex, where there is a spherical wavefronts incident on this lens, and it will make these spherical wavefronts into planar wavefronts, plane wavefronts. This is called dielectric antenna, okay. This is a dielectric lens, so it is a dielectric antenna. Now coming to the metal plate lens antenna. This is a metal plate lens antenna where there will be a concave, like plano-concave. Here also spherical wavefronts will incident, and still it will make the wavefronts into plane wavefronts. But this is metal plate, okay. So this is slotted array, low side lobe antenna for this. So this is slotted array, one of the example here, and this is a parabolic torus reflector. So now coming to radomes. What is radomes? Radomes are basically they only serve the purpose of protecting the radar system inside it. So it is like a protecting shield, that's it. From environment conditions, it will protect this inside the radar, so it will protect the radar, that's it. So this is what about the radar antennas. I hope you like and you gain some knowledge. Thank you for watching. If you didn't subscribe, do subscribe, like, share, and like the video. Thank you for watching. Goodbye.